we continue our discussion on modular arithmetic, and this lecture particularly we will see how the addition and multiplication gives a particular type of algebraic system. Actually, these as the example or modular operation as the example already we have discussed for our group ring, and now we see in general that how these properties are giving the particular type of algebraic systems. So, again properties of modular arithmetic. So, this modular arithmetic, as already I mentioned, will consider the mainly the addition and the multiplication. Okay. Now, and we will see the, if we remember that whenever that we have defined some algebraic systems like group ring, some general properties we have checked, and based on those properties, what are those properties like commutative, associative, whether additive inverse exists, additive identity, or the multiplicative inverse exists. Based on that we have defined some algebraic systems. Now, so now we see, or we first prepare some our addition modulo table. That means some table with the operation as the modular addition. Let we take one example of, and with this example we define that thing. So, addition and multiplication of modular arithmetic, we take the modulo say 8. Okay. Now, modulo 8 means that my set can be only 0, 1, 2, only 0 to n minus 1, 4, 5, 6, 7. Okay. So, now if we make the addition table, okay, first we do the addition table. So, I write that 0 because my set will be 0, 1, 2, 3, 4, 5, 6, 7. Here also okay, this is my addition modulo 8. I am taking, this is my addition and multiplication modulo 8. So, this is addition modulo 8. Now, how we do that thing? That if we know the addition, this is if A and B, say if this is my set S, then A and B belongs to S, then A plus B modulo 8 will be taking. Okay. That is the modulo. That means, I will add two numbers and will take the remainder when it is divided by 8. Now, A is 0 to 7, A can be 0 to 7, B can also be 0 to 7. So, we will be adding these two numbers and taking the remainder by dividing it by 8. So, 0 plus 0, it is 0, it is 1, 2, because if we add all the A plus B, that will be less than 8. So, the remainder will be the same thing. Now, if it is 1 plus 0, it is 1, 2, 2 divided by 8, remainder will be 2, 3, 4, 5, 6, 7. Now, this becomes 7, 1 plus 7, 8. 8 divided by 8, this remainder will be 0. Similarly, I can 0 plus 2, 3, 4, 5, 2 plus 4, 6, 7, this becomes 6 plus 2. So, 8 divided by 8 remainder 0, 2 plus 7 9. So, 9 divided by 8 1. Similarly, now we can fill up quickly 5, 6, 7. Now, this becomes 0, this becomes 1, this becomes 2. Now, it is 4, 5, 6, this becomes 0, 1, 2, 3. Oh, this is 7 because modulo 8 I am taking. This is 4 plus 3, 7, 7 modulo 8 is 7, 8 modulo 8 0, 1, 2, 3. Now, 5, it is become 5, 6, 7, now 0, 1, 2, 3, 4, 6, 7, now this becomes 0, 1, 2, 3, 4, 5. Now, 7 is 7, 0, 1, 2, 3, 4, 5, 6. So, we see that it is, if I take that 0 plus 0, it is 0, 1 plus 0, 1 plus 7 is a, or 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3, 4 plus 0. So, if we remember that my A plus E equal to A, then E is my, E is additive identity. So, here for modulo 8 addition, the identity, additive identity is 0. Okay, addition I have written, so I can write identity element is 0. Identity element E is 0. Now, what about the additive inverse? Now, if we remember if sum A plus A dash equal to E or A dash plus A, now, then A dash is the inverse of, additive inverse of A. Now, we see that if we that okay 0 plus 0 is 0, see 1 plus 7 is 0, 2 plus 6 is 0, 3 plus 5 is 0, 4 plus 5 is 0. So, since 0 is my identity, so for each element I am getting, if I add, I am getting one element, just to add I am getting the identity element. That means, for each element of this set from 0 to 7, that one inverse exists. So, for when A equal to 1, my A dash is 7, A equal to 2, my A dash is 6, like that. So, my for all A I can write, then for all A belongs to S, S is 0 to 7, that additive inverse exist. Later we will tabulate that thing, what are the, we now remember. So, additive inverse exist. So, when we are considering addition modulo 8, so this is my addition modulo 8, you can write, this is my addition modulo 8. So, for addition modulo 8, these are the things I get, my identity element exists which is equal to 0, and for all A the additive inverse exists, because just now we see that thing. Now, we take the multiplication, we see the multiplication modulo 8. Okay. See multiplication modulo 8. Okay. The same thing, that since here modulo 8, so my S is 0, 1, 2, 3, because only up to 7. So, when I am considering the modular arithmetic, that how this multiplication operation operates on this set. Okay. So, this is my multiplication, and considering 0, 1, 2, 4, 5, 6, 7. Here also we consider 0, 1, now it is multiplication. So, I have to take that A into B modulo 8, and AB belongs to S. So, 0 into 0, because 0 into all this becomes 0, and 0 modulo 8 is 0. So, I write these are all 0. Okay. Now, if I multiply, then this becomes 1 into 0 1, oh sorry, it is 0, and 1 into 1 1, 1 modulo 8 1, 2, since it is multiplied by 1 only. So, all are less than 8. So, remainder will be the same when divided by 8. Now, it is 0, 2, 4 modulo 8, 6 modulo 8, now 8 modulo 8, 2 into 4 8, and 8 modulo 8 is 0. Now, 2 into 5 10, 10 modulo 8, remainder is 2, 2 into 6 12, remainder is 4 when divided by 8, 2 into 7 14, remainder is 6. Now, similarly 3 into 0 0, 3, 6 modulo 8 6, 3 into 3 9, 9 modulo 8 is 1, 12 modulo 8 is 4, 15 modulo 8 is 7, 18 modulo 8 is 2, then 21 modulo 8 is 5. Now, 4 into 0 4, 8 modulo 8 0, this is 0, 4, 12 modulo 8 4, then it is 0, 16 modulo 8 0, 4, 24 is 0, 28 is 4, 5 0, 5, 10 modulo 8 is 2, 7, 20 modulo 8 4, 25 modulo 8 is 1, 30 modulo 8 is 6, 35 modulo 7 modulo 8 is 3. Now 0, 6, 4, this is 2 because 18 modulo 2, 8 into 2 16 plus 2, 24 modulo 8 0, then 30, so it is 6, again 4 and 2, 7 it is 0, 7, 14 is 6, 21 it is 5, it is 4, 28, 35 it is 3, 7 into 6 42, 42 modulo 8 is 2 and 7 into 7 49 modulo 8 is 1. Now, we see that what will be my multiplicative identity. Okay. So, we see that if I consider 1, then I am getting the 0 into 1 0, 1 into 1 1, 2 into 1 2. So, I can write that A into E, some we know that operation, that A into E modulo n, in this case that A into E modulo 8 is E only, A only, that number only. So, E is multiplicative identity and equal to 1. That means, for multiplication modulo or multiplicative modulo 8 is 1. Okay. So, now we remember the definition of inverse. For multiplicative inverse, we see multiplicative inverse, it will be, we remember A into A dash modulo 8 should be E or E modulo 8. Okay. I write A into E dash is E modulo 8. So, now we see that E is 1. So, see for 0, okay, 0 is, since we can see that 0 is, if I multiply everything it will be 0. So, from 1 to 7, from 1 we are getting some identity, that 1 into 1 identity. See for 2 we are not getting any identity. For 3 we are getting identity 1, but for 4 we are not getting. For 5 we are getting one identity. For 6 we are not getting. For 7 we are getting identity. So, if I summarize, I can write that for we are getting multiplicative identity for A equal to 1, 3, 5 and 7. That means, we are getting multiplicative identity. I give a tick mark if I getting identity and I give a cross if I do not get. So, I get for A equal to 1, 3, 5, 7 I am getting, and for we do not get no multiplicative identity for A equal to 2, 4, 6. So, we can conclude, the conclusion is that conclusion, or if I tabulate first, conclusion is if A is relatively prime to n when I am taking multiplication modulo n then multiplicative inverse exists. Then multiplication or multiplicative inverse exists. Now, what is relatively prime? Relatively prime to n, that means A and n are relatively prime when there is no common factor between A and n. So, A and n are relatively prime when there is no common factor of A and n. So, if we see that when A equal to, say I have taken modulo 8. So, I am taking mod 8 operation or modulo 8. So, my n equal to 8, and when I take A is 1, that means 1 and 8 other than, so factor of n other than, better I write other than 1. See, for 1, 3, 5, 7, this is, so 1 and, so A equal to 1, okay, A equal to 1 and n is 8 always. So, 1 and 8 they are relatively prime, we are getting that some inverse is 1 only, okay. We are getting that A dash equal to 1. When A equal to 3, we are getting A dash equal to 3, since 3 into, because 1 into 1 modulo 8 equal to 1 modulo 8, and 1 is my identity. 3 into 3 modulo 8 is my 9 modulo 8 is 1 modulo 8. What about A equal to 5? Is 5 only, because 25 is 25 should be the 5 into 5 8 into 3 plus 1. So, A dash equal to 5. So, 5 into 5 modulo 8 equal to 1 modulo 8. Then A equal to 7, we get A dash equal to 7, and this is 7 into 7 modulo 8 is 1 modulo 8. I think 1 we can see here, 7 into 7 we can, if I explain, this is 49 equal to 6 into 8 plus 1. So, when I will be taking modulo, and it will be 1 only, because it will, there is no remainder here. So, 49 modulo 8, it will be 1. So, 49 modulo 8 equal to 1 modulo 8. Similar thing for other 3 examples. So, now if we tabulate, we write that I have taken the set 0, 1, 2, 3, 4, 5, 6, 7. Since we are taking the modulo 8 addition and multiplication, 8 and modulo 8 addition and multiplication. So, the previous 2 examples, what we see that if we now write the A, the additive inverse and the multiplicative inverse. Okay. Okay. So, A can be 0, 1, 2, 3, 4, 5, 6, 7. I take the additive inverse and multiplicative inverse. Then what we have seen, 0 additive identities. So, in I must write this to my additive identity is 0, my multiplicative. We must remember that we are taking modulo 8 operation, multiplicative identity is 1, that earlier we have seen. Multiplicative identity is 1 modulo 8, 1. So, we have seen the additive modulo 0, because it is 1 plus 7 modulo 8 is 0, 2 plus 6 modulo 8 is 0, 3 plus 5 modulo 8 is 0 modulo 8, 4 plus 4 modulo 8, 5 plus 3 modulo 8, 6 plus 2 modulo 8, 7 plus 1 modulo 8. So, additive inverse exists, what earlier we have seen. What about multiplicative inverse? Since we do not consider 0, because that we know that there is no 0 divisors. So, we will multiplicative inverse does not exist. Now, for 7 we get the multiplicative inverse 7, because 7 into 7 is the 49, and just now we have seen that 49 modulo 8 is 1, but for 6 it does not exist. Then for 5 it is 5, this is sorry, these are A is this one. So, we are taking multiplicative inverse of 1, we have made some mistake. We are taking multiplicative inverse of 1. So, multiplicative inverse of 1 is 1 only, 1 into 1 modulo 8. 2 does not exist, 3 it is 3 only, then 4 does not exist. For 5 it is 5 only, for 6 there is no multiplicative inverse, for 7 the multiplicative inverse is 7. And we have already concluded earlier, the conclusion we have made that if A is relatively prime, with n, that means for my 1, 3, 5 and 7, then only we get the multiplicative inverse. And if they are not relatively prime, that means my A, if A and n are not relatively prime, then multiplicative inverse does not exist. And that is for A equal to 2, 4, 6, because 2, 4, 6 and 8, n equal to 8, they are not relatively prime, they have some common factor. So, it is there. Now, these will give us another algebraic system, it is called the field, what we will be talking in the next lecture. So, that means if multiplicative inverse is there. But if we remember that when we have read the ring, now if we see the properties of ring and properties of ring, what we have seen when we have seen the ring, that if we consider the addition modulo and the multiplication modulo 8 or some modulo operation, modulo arithmetic, the operation is addition and multiplication modulo n, general I am writing modulo n. Then set, obviously my set is 0 to n minus 1, already I have discussed because remainder only. Then what are the properties it holds? The first property holds is commutative laws. Okay. So, the properties are, commutative laws both for addition and multiplication, that we know that if it is x plus n modulo n, we remember that x plus y modulo n is y plus x modulo n, and same thing for multiplication, x into y mod n is y into x mod n. Now, it is my associative laws. We remember that now x, y, z we consider, and we can write that x plus y plus z modulo n equal to x plus y plus z modulo n, and I can write x plus y into z modulo n is x into y into z modulo n. Now, my distributive laws. We know the x cross y plus z modulo n, that will be the x cross y modulo n plus x cross z modulo n mod n. Or I can write together this mod n because it is same as that of, if we remember the multiplication rule, x this plus a additive rule, this is same. I can take this mod n and I can write x on that side also. So, if it is identities, okay, we go to the next, we continue. So, if I take the identities, already we have seen the additive identity 0, is 0 mod n and multiplicative identity is 1 mod n, and that it exists because 0 and 1 always be the set. Now, okay, 4, so this is my 4 and 5 is the additive inverse. So, what we have seen, that additive inverse exists, the additive inverse exists when we have taken the modulo n operation, modulo n addition exists for modulo n addition. So, it is a ring or commutative ring. So, my modulo arithmetic, modulo arithmetic operation, the addition and multiplication, two binary operations, the way the ring we have defined, two binary operations, and multiplication, the modulo is, or modulo n, we are taking modulo n and it is operated on set 0, 1 to n minus 1 and it is a commutative ring, because for multiplication also it is commutative. But what we have seen, the multiplicative inverse we cannot tell that for all the elements, only those elements which are not relatively prime, that it is they are inverse exist. But if they are relatively prime, that means common factor exists between a and n, then no multiplicative inverse exists. And this particular property when we will consider, then it becomes a new algebraic system called the field. So, next lecture we will discuss, we will read about the algebraic system field. That means, we will see that when multiplicative inverse, that property is satisfied when and how we can form that type of algebraic systems and their properties. So, with this we end our discussion on the modular arithmetic operations.